Welcome to the Lagrange point YouTube channel. That's what it feels like. I feel like I've done so many Lagrange point videos that I should make a whole channel, but I really want to get to a couple more videos, and then I'm probably going to pause because I have other work to do. So I've used this picture before, but I'm going to give you a super brief introduction to Lagrange points, and then what I want to do today is do a Monte Carlo calculation for a whole bunch of different Lagrange points to see if it's stable or not at the L2 Lagrange point. So here is a binary star system, and I have picked masses such that it's clearly orbiting around a center of mass. Both of them are orbiting. Okay, so if you pick like the Earth and the Sun doesn't move, or it doesn't noticeably move. But this is more interesting. So in this case, I have mass m1, m2 separated by a distance capital R, and I can calculate the orbital radiuses and the orbital velocities for these two masses such that they're in a stable circular orbit. And that's what I did over here. Now, if I put a low mass point right here at L2, well, in that case, I can get this to have the same angular velocity as these two. These are going to move in with an angular velocity. It can have the same angular velocity because even though it's further away from the center of mass, this has two forces acting on it, right? There is a gravitational force due to mass m2 and a gravitational force due to m1. And so that makes it a larger total force, and it can move with the same angular velocity. So the question is, how do you find that location? And the answer is to just say, well, I know the force, right? Because it's the distance between here and there for that force, this distance for that force, and the circular is the centripetal acceleration deals with this distance. And I know the angular velocity is the same as that one. So you get an equation that looks like this. It's not this because this is this one. And it's not easy to solve. Okay, where R1 and R2 are the distances of those two things. And then so you can solve it with some numerical methods, and that's what I've done in the past. But what I want to do today is to show that this is unstable. I've already shown that because it's hard to make even one complete orbit and have it stay there unless you get a very, very precise calculation. But I want to make a whole bunch of points there and see what happens. Okay, so here's what we're going to do. Let's put M1, and it's going to move around a circle like this. And then I have M2 over here. This is M1. This is M2. And then here I'm going to put a bunch of points right there. But let's just deal with one for right now. So here's what we need to do as we model the motion of this around here, because I have a program I'm going to modify, but I want to put a whole bunch of points. So we need to think about what I need to do for each point. Number one, I need to calculate R1 and R2. So this, I'll call this as R1, just for now. I really should call it RA1 or something, because let's call it that, because this was R1. And I need to calculate this distance. We'll call this RA2. I need those vectors because I need to calculate the total gravitational force on this, where the gravitational force FA1 is going to be negative G M1 MA over the magnitude of RA1 squared times the unit vector RA1. So if I know this vector, I need to find the magnitude of that vector, and then the unit vector is the vector pointing in that direction. So I can when I square that and take the magnitude, it's not a vector anymore. So that's the mass of star 1, that's the mass of that object here, and that's the gravitational constant. But I do get a vector. And then I can do the same thing for mass for star 2. FA2 is going to be negative G M2 MA RA2 hat over the magnitude of RA2 squared. And that's the net force. Now what do I do with the net force? Once I have the net force, I can say F net equals delta P delta T. This is the momentum principle. This says that the net force on an object changes its momentum. And I can write that, and this is the momentum of the object A. So I can write that as P2 minus P1 over delta T. I can solve that for P2. I get P2 equals P1 plus F net delta T. So this says that, this is wrong, right? Because this says that I can just take that net force, multiply it by a time interval, and get the new momentum. And that only works if Fnet's constant. And Fnet will only be constant. We can approximate Fnet as constant if delta t is small. And so that's what I've done before. But this is the same process I need to do for each, if I have a whole bunch of masses, each of these masses I need to do the same thing. So calculate R, calc R1 and R2. I'm just going to call them R1 and R2. Calculate the force on each particle. Update the momentum. And then I need to also update the position. So I can say RA2 equals RA1 plus P2 over MA delta T. This comes from the definition of the average velocity. So I need to update RA, let's call it. And so I need to do that for every single element in here. If I have 10 pieces, I need to do that 10 times. I need to do all those. And so I don't want to do that 10 sets of code. Instead, I'm going to use a list. A Python list where I'm going to put different objects in there, and those are all going to be in objects in a list. And so I can just go through the list and update them. And that's what I'm going to do. Now, there is one other thing. How am I going to distribute these masses? I'm going to make some random. I could put them just at certain positions, but I want to randomly position them. So what I'm going to do is to calculate this value, RL2. That's the location of my best location. And then I can just add some uncertainty to that. So I'll say, let's say delta R. I'm not sure if that's going to be the best variable. It's going to be a vector dx dy 0. So I'm doing this in the xy plane. And I could have had them in the z direction too, where this is going to be a random number. And so what I'm going to do is just take some percent of this value, let's say a 5% difference, maybe 10% difference, I don't know. And then use random numbers to generate those. So I'd make all these points. They'll all start with the same angular velocity as this. But then with that angular velocity, I can give them an initial momentum. So they're in initially a circular orbit with the right thing. But we'll see what happens as they evolve. Okay, so let's jump over to Python and let's see if we can make this thing work. I was going to write this code beforehand, but I didn't. So we're going to do it live. And if it turns out terrible, it turns out terrible, right? Okay, so this is code that I have here for something that I've already worked. I've made a copy event called a Monte Carlo Lagrange point 2. And so these are 2 stars, 2 times 10 to the 30th, 1 times 10 to the 29th, separated by 1 AU, and then they're going to orbit around, and this thing's bouncing up here, and it's really bothering me, so I'm going to quit this. Sorry about that. Oops, not that. That's fine. Okay. So we're good. We're still recording. Okay. So let's just run this and I'll show you what happens. So this is one mass at the point L2. You can notice that both both stars are orbiting a common center mass, and it's fairly stable. So I calculate some stuff here that I don't need to do, but what I want to do is change that one point into a list. Okay. So let's just get one point in there in my list. I'm going to put one point at the center of mass, at the best value for L2, and then I'll let it evolve and see what happens. And then we can add some other stuff. So I'll include a link down below about how to deal with lists in Python. But so far what I have here, this is just stuff for the binary stars. That's all for the binary star. That SP is there just so I can space out the camera. There's other ways to deal with the virtual camera, but I didn't want it to zoom out as the thing moved around. So I put a little point there that's really tiny. There's my T, my time step. This calculates the location of the Lagrange point for that binary star system. So I give it mass 1, mass 2, and the distance between them, and it calculates it for that. That's all that. This data is for something else. RT. Okay, so this is my object that I want to replace, ball 1. So let's just go ahead and delete some of this stuff. I don't need theta because I'm not doing that. I do, let's just say, what should I call it? Balls. It's an empty list. So I use these square brackets to denote an empty list. Now I'm going to add one item to that list, and then I'm going to model it. And after that, all I have to do is add more stuff to the list, and it should work. So let's say this. Let's calculate. I already calculated RT, right? RT is a location of the best location of a Lagrange point that I could get. So I don't want to put a ball. Instead, I'm going to say balls equals balls plus. Someone always told me to put spaces here because it looks better. An element. And that element is going to be this sphere. So I'm actually going to not make ball 1. I'm just going to add a sphere to my list. I can do that. It's going to have a trail. Should I have a trail? Let's turn the trail off. I kind of feel like make a trail, but don't make it. Let's just turn it off. We can turn it back on later. So it has a position vector. It has a radius. It has everything. Okay. I also need to give it a mass. And so I did that down here, but I'm just going to say, I can put that right in the definition of the sphere. I can say m equals 1,000. I can give it a momentum, right? So I'm just going to say this. P, I'm going to copy this. So P equals, I think I can do, I'm not sure if I can define it this way. That's just not. Okay. So I need to give it a momentum. So let's do that. So now I will say balls 0 dot p equals balls 0. So balls 0 is the first element in the list. I'm going to change this later on, but I need the mass times that cross product of this position, which is going to be balls 0 dot pos. So vector 0, 0 omega is the angular velocity for this system. And if I take r cross omega, I get the velocity. So that sets the momentum for that. So all this stuff I can delete. So I don't have ball 1 anymore. I have balls. It's a list with only one item in there. I don't know if I need these, and it doesn't make sense because I don't have balls. So let's just delete that. This stuff is just to show. So let's just delete all that stuff. Okay, so now I get down to my important thing. So R is the vector from star 1 to star 2, and I need that to model the motion of those two stars. So I don't want to change that. But R1, 1, I do need to change. So let's say, I'm going to write it like this. For I in balls. No. I need to say it like this. For in, let's say, for I in range len balls. I think that worked. So this will go through the number of, right now it's only one thing, right? There's one item in balls. And so I is just going to go from to 0. But now I can use that index to kind of reference the ball. I could do a different way to go through that list, but I think this will be the best. So the first thing I need to do is to calculate RT1. That's going to be the vector from the ball to the star. So it's going to be balls I dot pos minus star 1 dot pos. RT2 is balls I dot pos minus star 2 dot p, not star 2 dot pos. So that's just replicating this stuff right here. So I can delete that. Now the next thing I need to do in my loop is to calculate the force. So I'm just going to do this all in one step. I'm going to say F. I could do balls. Let's do ball FT. I don't know why. I'm just going to copy this. Except I'm not going to say M1. I'm going to say M1. I'm not going to say ball 1. Balls I dot M. Norm RT1 divided by mag RT1. Then I'm going to say minus this one. I got the minus sign there. And then I'm going to just change it to RT2. This is not the best way to do it. There's more elegant ways to do it, but the best way is the way that makes sense to you. Balls I dot M. I think that's good. Okay, so I calculated the total force. So that's this right here. That force right there is the force for the stars. I can't get rid of that. Ball 1 dot P. I can do this. Let's put that up here. Balls I dot P equal balls I dot P plus Ft times dt. So that updated that momentum property of ball I from its force that is calculated. Now I'm going to also update the position. So balls I dot POS equal balls I dot POS plus balls I dot P times dt divided by balls I dot M. So there. Now I already did this. I don't need to do that again. I already updated the position. I did it out of order, but I don't think it matters. And that should work. So it should do the same thing. I'm starting with the same position and everything. Unless there's an error, it should do the same thing that I did before. It's just that now I have a list of one item instead of a whole bunch of items. But if it works for this, then I can add a whole bunch of items to that list and it should be fine. So let's see. I'm not 100% sure this is going to work. See? Didn't work. Missing a right parentheses. That's not so bad. Okay. So up here, we're down here. Cross product. See, I have vector. I need another parenthesis right there. If that's all it was, I'm just going to be so impressed with myself. I usually make mistakes. Oh, there it is. And it didn't make a trail because I've turned off the trail. But winning. Okay, so now what I'm going to do is up here, I'm going to add some more things. So I'm going to say n equals 4. So I want to add 4 items to my thing. Now I'm going to say n equals 0. That's the number counter. Let's see, while n. I like to do it this way. While n is less than n, I'm just going to do this. Print n equals n plus 1. So that we're just going to print that out just so you can see how it works. So I have 0, 1, 2, 3. That is 4 items, making sure everything works. I get a little skittish sometimes. Okay, so now what I want to do is to generate a random number for the new location of a new ball. So I know RT is this vector from here to there. So let's say 5% of that. I want to have a 5% range, and I just picked that value. So let's say DRT. That's going to be my range. That's going to be RT times, I said 5%, 0.05. That's 5%. So that's my space, right? So now I'm going to generate a new item. So let's just say balls equals balls plus, I'm going to have this whole thing right here. Let's just put that same thing up here. I didn't put the... and let's call this RTT. And let's find out my new position. So let's up here, I'm going to say RTT equals vector. Now, I can generate a random number between 0 and 1, but I want a random number between negative RT and RT. So this is going to be DRT times random so it's going to be, I think there is another way to do this, but I'm actually going to say times 2 times random minus 1. So random could be 1 to 0. So if it's 0, I get negative 1 No, I need to be 2 times, so that would be -1. Would this be -2? -2. So random -2 would be, no, that's not it. Why did I get this wrong all the way? So random is random -1. So random could be between 0 and 1. But I want to go from 0, I want to go from 1 to -1. So let's say this is going to be 2 times that. Yeah, 2 times that, -1. So if random is, yeah, if random is 0, I get -1. If random's 1, I get 1. Okay, that works. And then I multiply it by this DRT. So now I get a value between DRT and negative DRT for my x-axis. And now let's do the same thing for the y. I can just copy that. It'll be a different random number. And then 0. So, and then I assign that down here. So that's good. And then I need to, that makes all the balls. Okay, now I feel like I want to go back and change this up. So I made that first ball right there. This just adds in more balls to that. So now I can say this. For I, and same thing, for I in range len balls. I want to go through the whole element again. I'm going to reset the momentum. So now I'm going to say balls I dot p equals balls I dot m times cross balls I dot pos vector 0, 0 omega. Yeah, so that sets the momentum for each one. Yeah, so I don't need to do it up here. I just made one ball right there, and then I added 4 more balls right there, and that's it. I think this might work. Now down here, nothing changes, right? Because now if I have 5 balls in there, it doesn't really matter. Let's just see if this works. If this works, I didn't save it. If this works, I tell you people, I need to give myself a high five. But I'm not giving myself a high five yet. It doesn't work. I don't know if it works. See? A variable is not a number. A variable is not a number. It's got to be somewhere down here. In random. Let's just print. Let's see if it even gets here. Print RTT. It did. Okay. That's good. So let's see if it gets down here. Print in. Did. Okay. So it must be right here. For I in range length of balls. Balls.I equals balls.I times m times cross product balls I.pos vector 0, 0, 0. Let's just try this. Print balls I.p. Not a number. So printed that first one, but then it didn't. So balls I, what about POS? They do have positions, right? Okay, they do have a position. Oh, okay. So the problem is I calculated RT, but I need to add that to my initial position. I don't think that's the only error. So up here, RTT is this. So I'm going to say RT plus. So RT, because I want to vary the location based around that Lagrange point. I don't think this is the problem, though. Oh, wait. I'm a vector of a vector. So that first momentum is fine. It's the, wait, am I printing balls.pos? Oh, RTT is a vector. balls I.pos. Print that. I printed the first one is fine, but the second ones are not. Balls equals balls plus sphere RTT. RT is what? A vector. This is what happens when we don't do things live. Okay, that's fine. I don't know why that's. Print RTT. And let's turn this print off because that looks like I'm printing the position, but it's a vector, which is weird. Okay, so there's my first. RTT. That's really weird. Okay, so there's my first one. And then I'm getting all this weird stuff after that. Oh, this. Let's go down here. Okay, so I added balls. RT vector DRT random. That should work. 0. Oh, please don't make me abort this video. I was so close. I was almost giving myself a high five. Remember that? I didn't. I was like, I can give myself a. Okay. Balls equals balls. Sphere RT. No. See, I'm getting this. I'm just getting weird stuff. Okay, let's see. So let's down here. Okay, let's go back up. Okay, this. Let's just print this. Print balls 0 dot pos. And let's turn off all of the prints. Do I have another print in there? Burn it. Okay, that one's fine. Let's turn this to n equals 1. And let's print RTT. Okay, so there's my first one. But now my second one is this weird... No. This thing is weird. Look at that. What the heck is going on there? So ball... what about this? Print balls 1, that should be the second one, .pos. Just to make sure that is the right thing. Okay, but so now I have this number and a vector in there. Okay, so RTT, I did the same thing. Balls equals balls plus sphere RT. I wonder if that's the problem. Because RT is, no, RT. RT is a number, right? Oh. RT is a vector. RT is a vector, that's fine. You notice I'm sinking down in my seat because I'm like, oh, this is not working. RT. RTT is RT plus vector. See, let's just print this. Let's just get rid of this. Get rid of this. And get rid of this. And just print RTT. No, let's just print. Let's print this right here. DRT. Oh, I got it. RT. This should be mag RT. Okay, because I was multiplying. I was using. That's what I did wrong. Okay, so let's see what happens now. There. There. Okay, now I can change this back up to n equals 4, and everything's working. I don't even need to print all this stuff out. Don't need to print that. Don't need to print that. I like it. Let's make them a little bit bigger. R divided by 40. R divided by 40. Okay, now Now, I mean, if it works for 4, it should work for 10, right? It's kind of art. I feel like it's art, right? Let me move this thing down here so you can see fully. Okay, so let's run it. Let's do 30. And now the other thing I want to do is to, so you see they don't stay together. Now the goal here is I want to do this again for Lagrange point L4 and show that it does work. Let's make this 1% variation. Now they're all clumped together, but they spread out. I mean, I don't know if this is 100% legitimate, but it looks legitimate. There's that one, look right here. That's that one point that I put at the stable point, and it stayed there. But all the other ones didn't. So unstable. I think I've shown what I wanted to show. I'm pretty happy with this. So there you go. Don't let me forget. I'm going to put a link to lists down below. I'm going to put a link to the code below. This is part of a playlist on Lagrange points, so you can check them out. I really want to do one more thing, and hopefully I can do that today, and that's going to be to do this exact same calculation, but put them at Lagrange point L4, which is supposed to be stable. So if that's the case, then these should, like, even though they start off far apart, they should all kind of, like, stay there. So, all right. Cool. I'm glad we fixed our problem. See, you just got to keep at it, put print statements in there. You can figure out what the problem is. Printing statements help you kind of diagnose the problem. And that's what's kind of fun about doing these numerical calculations. Plus the art. I guess one other thing, actually one thing more. Let's do this. Make trail equals true. Let's just see what that looks like. True, and let's make it back smaller because those are kind of big. And then down here, I got to do the same thing. Where to do that? Add the balls. That was it. So that 60. It's going to look crazy though, I think, because they go so far off. Oh, I like it though. And it's in 3D, just so you know. All right, cool. Okay, that's it.